Hey, welcome everybody. Dr. Daniel Barth back with you again for the 67th episode of How Do You Know? And as always, every week, this book is brought to you by Star Mentor. If you've got someone on your Christmas list who has a telescope, know what to do next, how to learn to use the telescope more effectively, I recommend Star Mentor. I wrote it for you. This book contains more than 50 activities to teach you how to maneuver the telescope, how to learn the sky, how to find the constellations, uh, exciting targets for each season of the year, and a great Christmas gift. We also talk about a book every week that I'm reading. So, a couple this week. This is Constants of Nature by John D. Barrow. The late Professor Barrow, you've heard me talk about him before, the anthropic episode and other things. Barrow is a very deep thinker and a wonderful scholar. And his book, Constants of Nature, talks about what are the fundamental numbers. In other words, what things in the universe must be as they are, or life would be impossible, our universe would be impossible. So really fundamental things. And this is the kind of book that I like to read 5 or 10 pages, and then I put it down and think. I go, this is a great book if you're deeply into astronomy, cosmology, the Big Bang, those sorts of things. Something to look at. The other book of the week that I'm going to recommend to you. This is a Manual of the Slide Rule by J.E. Thompson. This is put out. This is a Wildside book, and this is a reprint from a book originally published in 1930. And yes, as you know, I'm a nerd, and I have a slide rule. And yes, if you ask, yes, I do really do math on a routine basis on the slide rule. This is a 1959 era slide rule from Pickett. You can find one on eBay for about $10 or $15. And this lovely model is almost 65 years old. It still works perfectly. I have rarely had an electronic calculator go more than 7 or 8, and it still functions properly. And certainly this one has required no batteries, no power, and nothing other than the knowledge of the user for 60 years. People say to me, Doc, do you like books or ebooks? And I must admit, as you can see in my background here, I have great fondness for print books. Ebooks have to be reformatted and converted every few years as the standards for ebook files change. Print books, centuries hence, will be readable, provided they are saved from the tooth of the moth and the rat, etc. These books, paper books, will be readable to people for centuries to come. Anyway, so let's go ahead and talk about the topic of the week, which is set the standards. And we have a quote of the week this week. I don't know if we'll continue to do this, but the universe, this is according to John Barrow, the universe is 10 to the 60th power Planck times old. The Planck time is the smallest possible quanta of time. What is the shortest possible unit of time? And we talk about the quantum theory says everything comes in a smallest possible package. Energy, light, the photon, of course, and time also comes in Planck time units, which are very, very small. Life appeared on Earth when the universe was 10 to the 59th Planck times old. Life is a recent arrival, and many of you may know the analogy: if the entire 4 billion year history of life was compressed into 24 hours, human beings arrived on December 31st at 12:59, about 50 seconds, give or take. So we are very recent arrivals, and we haven't been here very long. Many people talk about something called the Fermi paradox, which maybe you've heard of that. The Fermi paradox says basically, well, gee, if life is common, why haven't we heard from somebody yet, right? One of the very real possibilities to that is how the question is, how old does the universe have to be before life can appear? And if we are one of the very first species, then in fact we would not expect to have heard from anyone yet. If the universe will get hundreds of trillions of years old, that will be a lot more time for intelligent species to evolve and to reach out and contact nearby neighbors on a galactic or interstellar scale. So um, that's just something interesting to put a little bee in your bonnet as we go forward. So we want to talk about today, where do our standards for measuring come from? And we think about this, and it's kind of funny. You may know the story, oh, the inch was originally the length of the king's thumb, the foot was the length of the king's foot, a yard was for measuring cloth, and you held a bolt of cloth up by your nose and you stretched out as far as you could reach, and that was 1 yard of cloth. And of course, a tall tailor could give you more cloth. And for thousands of years, people have struggled to find standardized units of measure. If I'm going to buy wheat, or if I'm going to trade gold for goods and services, then how do I do that? I need a standard measure for how much grain is a unit of measure. I want to know that if I buy a unit of corn from one dealer or from another, I'm getting the same amount of corn. Why do we have coinage? Well, we have coinage because the government, which is in power, stamps a coin. It's a guaranteed measure. We have been off the gold and silver standard for a long time, almost a century. And that's a beer and pretzels conversation. But essentially, our coinage now is not based upon a valuable commodity. It's simply based upon the faith that we have in our government that controls the coinage and the currency. Right now, because we are not on a gold standard or anything else, the government can say, oh, well, we're going to increase the amount of currency in circulation. And so we'll print another several $1 trillion of currency and put it into circulation. And interestingly, this is one of the things that Newton did when Newton became famous. And the government wanted to take this famous man and have him in as part of the government. And they said, well, Professor, what would you like to do? And Newton said, let me control the mint. Why? Because the mint controls both the quality and quantity of coinage. And at the time in England, there was a big counterfeiting problem. How do you tell if a coin is really minted by the government? How do you tell if it's really pure gold or pure silver? And Newton changed the coinage, and he introduced things like milled edges, the little bumps you see around the edges, to make it more difficult for counterfeiters to produce coins. And he supervised the mint and the king's government to pursue and arrest and hang counterfeiters. And almost 40 counterfeiters were hanged under Newton's supervision of the mint for counterfeiting, because the king's government depended highly upon the royal economy, the economy of Great Britain, which depended upon the full faith that the public had in the currency. And so when we look at where these measurements come from, and we have this interesting little picture, and let me see if I can pull this up for you. Paul has it there for me. Very good. Thank you, sir. And we see this lovely page here. And this was included in textbooks when I was a boy. This chart or something very similar like it was included. Many people can remember having paper folders in school, and you would get a paper folder, and inside the paper folder was a list of weights and measures and conversions. And this is pre-metric. This is mid-1950s. And so we can see I'm going to slaughter the pronunciation, avoirdupois weight, and we see something like 16 drams makes an ounce. Where do we get that from? Well, drams are often a measure, and we hear dram laws for places of business that sell alcohol. You can't sell that much alcohol. We see things like, 437 and a half grains make an ounce. Where do we see grains? Grains are still today in pharmacy, grains of aspirin, or in ammunition, grains of lead in a bullet. And so we see 14 pounds is a stone. Our listeners in Great Britain and Australia, Canada will probably be familiar with the stone as a measure of weight. 14 pounds to the stone. It takes 2 stones to make a quarter, and 4 quarters or 8 stones, 112 pounds makes 100 weight. Why 112 for 100 weight? And this gives us 20 hundredweights, or the avoirdupois pound, of 2,240 pounds to the ton. The standard ton now is 2,000 pounds. The metric ton, TONNE, is 1,000 kilograms, which is closer to the hundredweight. Length measure, liquids, 4 gills makes a pint, 2 pints makes a quart, 4 quarts or 8 pints makes a gallon. 2 gallons is a peck, 4 pecks is a bushel, and 8 bushels makes a. And you get into all sorts of things like square measure. Square inches, 144 makes a square foot. 9 square feet makes a square yard. 30 and a quarter square yards makes 1 square pole. 40 poles makes a rood. 4 roods goes ahead and makes an acre. And we have all sorts of things. 640 acres makes a square mile. 10,000 square lengths makes a square chain. And you're like, oh my gosh, who would remember all of this stuff? And indeed, you can see why, if you were going to do various measures. An interesting one that's still used today, the knot, right? How many knots? We talk about the speed of a ship in knots. And the knot has nothing to do with a knot on a rope. It has to do with the nautical mile. That's the abbreviation for knot. And so we look at this crazy thing and we realize, we've got, how many knots does a ship do? That's nautical miles per hour. And a nautical mile, 2,025 yards, whereas a standard mile is something like 1,760 yards. Why 2,025? I don't know. All of these have meaning, and they were all developed. And the interesting part is, through the advent of World War II, industry had own standards of measure. If you were going to be a tailor or an engineer, et cetera, you had your own standard of measure. Today, we're not used to multiple standards of measure. If you live in the United States, one interesting thing is many of us have 2 sets of tools. And you might like, why would you have 2 sets of tools? That's because we have the SAE, or Society of Automotive Engineers, which measures things like nuts and bolts and screws with imperial or American standard measures, inches. And then we have the metric. So I have in my garage 2 sets of tools. Why? Because on my tractor, on my sports car, which I do the maintenance on both of them for the most part, well, guess what? There's bolts and things on there that are metric. There are bolts and screws on there that are not. And then we have torques and other sort of tools. So we have this strange thing. But World War II, we had this great industrial leap forward in industrial design and manufacturing. And we had a great push to standardize, because the government wanted to order parts from one manufacturer or another. If you're getting Jeeps from Willys, you want to be able to order fenders and tires from whatever manufacturer could produce them for the war effort, and everything need to be standardized so that a part made by one company would bolt on nicely to a machine, an airplane, or a tank, or a truck made by another. And so we had this great drive to standardization. But all of these measurements are human scale measurements. One of the things most of us don't realize is that the metric system comes to us from the French. And during the French Revolution, they had this great thing: we're going to get rid of everything that's old and we're going to have everything that's new. And the French gave to us the metric system. And they defined the meter as being 1/10 of measured distance from the Earth's pole to the Earth's equator. Well, this is an interesting idea, and it gave us an anthropocentric measurement. In other words, a human scale measurement. A meter stick is something we can hold in our hand, and we can put it down on the floor or a desk, and we could say meter and kilometer and millimeter and centimeter, and they're all useful because they match essentially the size of a human body. A human is rarely more than meters tall, rarely less than one, and the things we measure in meters and millimeters and centimeters, all in kilometers, all measure our human standards of distance. Kilometers work just fine for the distance from one town to the next. How deep is the ocean? Meters work fine for building roads and houses and bridges. Centimeters work and millimeters work great for most of our engineering projects. And we think about this and we go, oh, these things were made for us, quite literally. The kilogram originally comes from the gram is the base unit of measure. The gram is 1 cubic centimeter filled with water at 4 degrees centigrade. The idea being, anywhere in the world, you could have a standard meter stick and you could measure yourself out of a box that was 1 cubic centimeter, and you could put water in it, and you could have hey, book, nice to hear from you. You could have a standard unit of measure that anyone, anywhere in the world could reproduce. The second, of course, comes from the amount of time it takes the Earth to spin on its axis. One rotation of the Earth gives us 1 day. 1 day gives us 84,600 seconds. Why? The old base 60 measuring system. Take the day, divide it into 24 hours, each hour into 60 minutes, each minute into 60 seconds. And so you do the math, slide rule in hand, and you go, hey, we got 84,600 seconds. Well, the problem with these very human measures, both their strength and their weakness. Their strength, they're made for us. Made life the way we live it, on our scale, our bodies, our planet, the distances between our towns, the sizes and weights that we use in trade and commerce and engineering, science, design. All our measurements are designed for us. And there's great sense in that. And what do we do if we want to look at fundamental measurements? George Stoney, an Irish physicist, thought about this, and back as far as 1874, he starts saying, what about, isn't there a universal measurement? And you have to remember the 1870s, the time of the great Mars opposition. People like Cassini and Schiaparelli and other scientists are looking at Mars, which is having the great close opposition of 1877. And the question of, is there life on other planets? This is a current topic of scientific investigation and debate. And so George Stoney says, well, if we contact these civilizations, how do we talk to them? Certainly, if we had a meeting with aliens and we wanted to establish communication, the first language is mathematics. You take the great novels of First Contact, the things like Football by Larry Niven and Jerry Purnell, The Mote in God's Eye by the same pair. You go ahead and you take a look at, any number of novels like this, and they all say, oh, the first thing we do, we start sending them numbers 1, 2, 3, 4, and then we give them things like pi, which establishes what base we're communicating in. And so, well, how do we communicate measurements? How do we say our planet is this big? It's this far from our star. It takes this long to go around once. He wanted universal measurements. And one of the things Stoney was passionate about, and he was many decades before his time, perhaps 50 years or more, he was passionate about the electron. He called it neutrine. I like electron better. But he predicted that there would be a fundamental amount of electric charge. Now, the atomic theory is a very old theory, thousands of years old, that posits that you take matter, I'm going to take a piece of paper and I'm going to take my scissors, chop it into smaller and smaller pieces. And the atomist said there's the smallest possible piece. And if you get down to the atom, you can't cut it any further. And the atom goes along with the theory of elements. And the element theory and the atom theory are actually separate, but they merged sometime over the years. And the idea you could have a smallest possible piece of anything, and you have fundamental substances, and the smallest piece of iron or sodium or hydrogen you could have was one atom. Stokes said electric charge is the same way. This is 50 years or more before Max Planck and Einstein and others started coming up with the quantum theory that everything has a smallest possible piece. And Stoney said, well, there must be a fundamental amount of electric charge where it's this small and there's no smaller. And so Stoney said, how are we going to communicate this to an alien species when we finally meet one? And he realized our units of time, length, and mass, which are fundamental to all of science, right? You think of the metric system, which is known as the MKS system, meter, kilogram, second. It's also known as CGS, centimeter, gram, second. And which of those is more fundamental? It's kind of odd because nobody has a meter, gram, second. An MGS system doesn't exist, which is quite odd, but there you go. And Stoney said none of these units make so. He wanted measurements which were made based on quantities and physical constants that any civilized, scientifically advanced species would know. And so he selected 3. He said, let's have G, which is Newton's universal constant of gravitation. G, ever units, G is always the same. Let's have C, which is the speed of light, and let's have E as the charge of the electron. And Stoney figured that any advanced civilization who was able to contact us would know about these things. They would have their own discoverer of universal gravitation. They would have their own discoverer of the speed of light, which is universal. And they would have their own discoverer of the electron. Now, keep in mind, Stoney is looking at this in 1874. This is before Einstein would show that the speed of light is constant for all observers. This is many decades before the electron was discovered, etc., etc. So Stoney is way ahead of his time. And so he develops these constants by combining these 3. And he comes up with these ideas and he says, here we go. Mass, the fundamental unit of mass, is the square root of the charge on the electron squared divided by the constant of gravity. And this gives us a very tiny number, 10 to the negative 7th grams. This is a 0 followed by a decimal, followed by 7 more zeros, and then a 1. And it's a very small mass. Length is even worse. Length is the constant of rotation times the square of the charge on the electron divided by the 4th power of the speed. The speed of light is 300,000 meters per second, so the 4th power is a hella big number. Take the square root of that, and you get a measure of 10 to the negative 37th meters. This is far beyond. These measures were far beyond the ability of anyone to measure in Stoney's time. Length, even worse. The square root of g times the square of the charge on the electron divided by the 6th power of the speed of light, and that gives you 10 to the negative 46 seconds. A decimal point, 46 zeros, and a 1. That's tiny. That's far beyond our ability to measure. And these things were so far beyond human experience. Nobody was doing any science or math or engineering with units anywhere near this scale. And so Stoney's ideas were interesting, and he presented them at very famous conferences on natural sciences, but he was pretty much ignored. People said, wow, that's cool, Stoney, but gee whiz, no one would ever measure in those units, because measuring something like you could say, oh, how much clay do I have, or how much corn is in a bushel? And if you're measuring it in units, the number is astronomical. And so nobody was interested. Well, there we sit for about 25 years, and along comes another great physicist, the German physicist Max Planck. Now, Planck takes up the challenge, and he says, well, why does he do this? Because in 1899, Planck founded the quantum theory. Many people do not realize, but in fact, Einstein was the scientist who discovered the first actual practical evidence that atoms are real things, and he discovered the first proof that the atom of light was a real thing, and this is what he got his Nobel Prize for. He never received a Nobel Prize for relativity. The interesting and arcane rules of the Nobel Prize Committee. But kind of the intellectual successor to atomic theory. The atomists, the ancient Greeks, who said, and they were thinking philosophically now, they were going, what's the smallest piece of something you can cut in? And there were people who said, no, the universe is continuous. In other words, you could keep slicing as far as you want. Some of you may remember Zeno's paradox. If you are away from a wall, and every time you move half the distance closer, move an infinite number of times before you ever touch the wall. And calculus resolves Zeno's paradox, but at the time he did it, several hundred years BC, there was no answer for this. Quantum theory basically said the universe is not continuous. There is a smallest fundamental particle, which they called atomos in Greek. And forgive me, friends, if I'm slaughtering the pronunciation. Atomos basically meant indivisible. You can't cut it anymore. Quantum theory says not just mass or matter, but energy comes in a smallest possible unit. And so this smallest possible unit, Einstein basically did an experiment with what's called Brownian motion. Some of you may remember this from high school. You take a dish of water, you put onto the dish of water a few grains of pollen, and you can look in a microscope and you see them jittering around. Why are they jittering? Einstein deduced quite correctly that what was happening is the molecules of water were bound randomly into the pollen grains and making them vibrate in random motion. And he tied that mathematically back to the energy and temperature of the water, first proof of actual atoms. Photoelectric effect experiment. Einstein took a charged bit of metal, two pieces of metal separated by a gap. On one of them, could electric charge jump from one to the other? Well, he found if he tuned the charge just right and he did it in the dark, that the charges would not jump. And as you increase the color or the frequency of light from the red end of the spectrum through to the blue, you could get frequency which would the electrons off. Go ahead and make them. We use this today, the electric eye or the photoelectric sensor. If you have a night light in your house with a little sensor that detects when it gets dark and it turns on the night light or the light in your yard, you are using Einstein's Nobel Prize winning device in your home, which I think is really cool. But Einstein proved that if the light wasn't high enough energy, if the frequency wasn't high enough, it wouldn't kick off an electron. So low energy light, like red light, doesn't kick off an electron. But higher energy light was blue, and Einstein proved that no matter how bright you made the red light, it didn't matter because the energy in the photons of red light were not enough to kick an electron off. We as astronomers know this because when we're out working with our telescopes, we bring in LED light. Any of you old enough to remember putting red filters on a flashlight? I am. I had a little L-shaped Boy Scout flashlight with a screw-on red filter. Why do we use red light? Because red light photons are low energy. They do not destroy the molecules of visual purple. In other words, don't damage your night vision. Why do we say don't use your cell phone as a light to read your map for when you're doing astronomy? Because cell phone screens are notorious for emitting mostly blue light. And yes, you can get a red light app for your phone. I have one on my phone where my phone emits only red light or mostly red light, and it's not as damaged. But I generally use a red LED because I can use a red LED. I can sketch, I can look at a map, and then I can go back to the eyepiece and my night vision isn't damaged and still see whatever I'm looking at, whatever nebula or cluster or etc. that I'm looking at. So back to Planck, he was suspicious, like Stoney, of units of measurement depend upon our local situation. He said the whole CGS, the centimeter gram second system, is based upon accidental circumstances. He said if we were different beings and grew up in a different planet, it would have a different period of rotation, a different orbital period. We would have all of these things would be different. And so Planck, like Stoney, wanted units of length, mass, time, and temperature. Planck adds temperature here. It's quite clear with his quantum theory that energy, whether you're talking temperature or units of energy for light, it's all quantized. He wants these units, which would retain, quote here, retain their significance for all time, all environments, terrestrial or otherwise. So in 1899, Max Planck is thinking about, if we need to talk to aliens, how do we do that? Well, Planck picked something known as H, or the quanta of action. This is now known as Planck's constant, and we use the italic H as the symbol for this. This is the smallest quantum of energy, or the smallest amount of energy you can have. You cannot divide it. It is, in effect, the atom of energy, if you will forgive me. Planck also incorporated K, or what's called Boltzmann's constant, because Boltzmann's constant K converts units of energy into units of temperature. And so with Planck's unit, we now have mass is h times the speed of light, excuse me, the square root of h times the speed of light divided by Newton's universal gravitation. And this gives us 5.56 times 10 to the negative fifth grams. This is very small, but 10 to the negative fifth grams is a 10,000th. That's imaginable anyway. Length became gravitation times Planck's constant divided by the cube of the speed of light. And we take the square root of that quantity and we get a very, very small 4.13 times 10 to the negative 33 meters. This is often referred to today as a Planck length. And the Planck length is something that is deducible by any scientifically advanced civilization, and it would be the same. We have it in a unit of meters, but no matter what units they put it in, the quantity of the Planck length, and I want to emphasize this, the quantity is the same. If I said the Barth unit of mass is based upon my sacred ball of clay, and I could convert this and say this is equal to 10.057 grams. But no matter what unit to express the sacred mass in, the amount of mass is always the same. This is the idea behind Tony's genius. No matter what units we use, the quantity, the amount is always the same. Carl Sagan's brilliant book, Contact. Many of you may have seen the movie with Jodie Foster. The book is really fascinating. I highly recommend it. Contact talks about how do the aliens get in touch with us. They send us information, and embedded in the information is how to build this device that will allow us to travel faster than the speed of light to reach them. And in fact, the machine, the design plans are in Planck units. So many Planck masses of uranium or titanium or whatever, things were so many Planck lengths long because the aliens knew that whatever units we used, that quantity was absolute for all time, all places, all eras. Temperature, time comes out to be the square root of gravitation times the Planck's constant divided by the fifth power of the speed of light. And this gives us 1.38 times 10 to the negative 43rd seconds. This is the Planck time. No smaller unit of time is believed to be accessible. What happened after the Big Bang? You can talk about 1 Planck time after the Big Bang. You can't talk about less than that because time, like space, like mass, like length, like temperature, is quantized. And there is a smallest possible. Well, for temperature, the result gets really crazy. Here, the square root of Planck's constant times the fifth power of the speed of light. Think about that. 300,000 meters per second to the fifth power. An enormous number. Divide Newton's constant of gravitation, and then that whole square rooted quantity divided by Boltzmann's constant, and you get a number 3.5 times 10 to the 32nd Kelvin degrees. We talk at the heart of stars being, a really hot star might be 10 billion kelvins. 10 kelvins is 10 to the ninth. And here we have a temperature in the order of the 32nd. This is believed to be the hottest possible temperature. Beyond this temperature, nothing could exist because the kinetic energy would be so enormous, everything would be reduced to a soup of quarks. And this massive 3.5 times 10 to the 32nd kelvins This is called the Planck temperature scale. And the Planck temperature scale goes from 0 to 1. This one absolutely fries me. 0 is absolute 0, and 1 is the Planck temperature. And so all temperatures are now a decimal fraction. They're a decimal amount, 0.0000 something. And if you get to the hottest possible temperature, you reach 1, and then the scale is done. That one just delights me, because not only do we exist at absolutely infinitesimally small temperatures, the difference between us and absolute 0 is insignificant compared to the temperature that biology happens at, and the top of the Planck scale of 3.5 times 10 to the 32nd degrees Kelvin. And so that's really interesting. The universe took a long time to get cool. Many of us know that, the temperature of the background radiation is about 3.5 degrees Kelvin. And that's fine. And we're like, brr, that's very cold. And yet, if we consider the Planck scale, we realize, the universe had to expand enough to cool down to biological temperatures in order for it to be. The universe had to be old and cold before life could ever exist. Now, no great idea goes unchallenged. We've talked about many times in this program. And of course, who follows Planck but one of his students and great admirers, Albert Einstein. And in his correspondence, Einstein talked about two types of constants. When we're talking about constants, we're talking about things like the speed of light, the electric charge, etc. He's talking about quantum theory. And although he spent much of his life arguing against quantum theory, he goes back to it's very funny, he won his Nobel Prize for basically advances in quantum theory, which he detested and fought for decades, trying to prove that quantum theory wasn't true. But Einstein said two kinds of constants. One are the apparent constants. Those are things which are what we call anthropocentric. We invent the meter because it's about the size of us. We invent the gram because it's convenient to us. We invent the second because it's based upon the rotation and period of the planet we happen to be on. And he said these things appear because we use arbitrary units that are handy. They're not fundamental, they're just handy. And then he said there's the real constants. And Einstein said real constants were simply numerical values. Now, this is funny because Einstein is not going with the mass, length, time, and temperature of Planck, or even the mass, length, time of Stoney. Einstein is saying, no. There have to be even more fundamental constants, which are just numbers. No units at all. Things like pi. Pi appears all over the place. If you've taken a class in physics, you're like, this is devil, because it appears in the most places, in formulas. Pi appears in the formula for the period of a pendulum. Why? Pi appears in things like you're calculating amperage and voltage and things, and electrical things like that, transmission. Pi appears in there. Why? Pi appears all over the place. It's a fundamental constant. E, the number E, the logarithmic constant, is in there too. Other constants include things like the Reynolds number. Anybody familiar with this? Reynolds number has to do with flow. If we have the flow of liquid or gas through a pipe, or we have the flow of water over the surface of a shark as it swims through the ocean, or the flow of air as we have a very aerodynamic new automobile. The new Ioniq 6 from Kia claims a drag coefficient of 0.22. Trying very much to have laminar flow. where things move in straight lines and there's no turbulence. The Reynolds number has to do with this pure number. There are no units. Einstein thought that apparent constants could be eliminated. This is one of his great ideas, like the unified field theory, which never really came to fruition, although he worked on them for the last several decades of his life. And he said if we knew enough about nature, we could just have these universal constants with no units and we would need nothing. And if people have objected and said, oh, if you look at a space-time diagram, the speed of light, and Einstein said he didn't like the speed of light because it was meters per second, distance over time. If you look at a space-time diagram, the speed of light is expressed as an angle. It's a pure number, no units at all. And so looking at all these numbers, Einstein said they're all relatively close to 1. And by relatively close, we mean that they are within an order of magnitude or 2. And if you think of things like 10 to the 32nd and 10 to the 32nd, these are enormous ranges. And Einstein said, no. All these truly universal, he believed, are essentially close to 1. And the other thing Einstein said, that real constants are not free. In other words, you can't make them appear different than what they are. We can take a unit of measure and we can say, oh, there's a Planck length, but we can express that in meters or kilometers or astronomical units. We can express them in any units we wish. Einstein said real constants are not free and depend on units at all. And so we can't choose for them to be different. No matter what system of measure we have, we can't make pi different than 3.14159, etc. Now, we have a different base than base 10. We could have base 5 or base 2 or base 12 or base 60, for God's sake, like the ancient astronomers did. And we could calculate pi in base 60. But no matter, hello from Belgium. Hello, Beatrice. Nice to hear from you. The lovely idea. And then there's Sentil. Hi, we're hearing from our folks around the world. I love that. Thank you. The idea of these constants that aren't free, no matter what language we use, no matter what system of, like pi and E and the Reynolds number aren't any different. Here's a comment from Osmosis. I've always thought the hugeness of space, the chances of a planet meeting us are rather slim. Yes, that's part, Osmosis, that's part of the Fermi paradox. And how would we contact them? And right now, as we understand it, the speed of light is fundamental. You can't go faster. And people have speculated for 100 years or more about could you in fact have a faster than light travel system. Much of our science fiction is based upon it, Star Trek, Star Wars, etc., etc. Yes, could that exist? Who knows? But again, we've talked about book says, the thing about SI is it's intense. Yes, book, but the base 10 is arbitrary. Base 10 is arbitrary. If we made it in the hexadecimal system, which is base 16, we could go ahead and just 16 characters, after which we start again. There's nothing special about base 10. Nothing at all. We have 10 fingers, and it's thought that base 10 comes from this, but in fact, base 2, binary, which we use in computers all the time, is base 2. It has 1, 0, and nothing else, which works great for transistors. Book is asking, is this what Planck used for his scale? Planck's scale uses the meter kilogram second system, the base 10 decimal scale. It does. The whole idea behind the work of Planck and Stoney and Einstein is that it doesn't matter if you're base 10, base 12, base 60, base 2, uh, or whether you're talking meters, grams and seconds, or if you have some other unit of mass, length, and time, no matter what your units are, the quantity of a Planck length that I measure is the same as any advanced civilization would measure it. No matter what units we use, the physical measurement is the same. If I said I wanted a bar that was 10 billion quantum links long, 10 billion links long, and that's I could hold in my hand, that bar would be identically long for any species that produced it, because it doesn't matter what their local engineering measurement units are. The fundamental Planck length is the same. And yes, talks about the quantum foam. That's the idea of getting down to space-time on the Planck length scale, and you can't get smaller than that. Yes, book says one is the hottest on the Planck temperature scale. Yes, it's strange where everything is a decimal fraction. I love it. It's delightfully bizarre, but it also fills a deep need. No, it's not arbitrary at all. It's simply, well, think about Celsius, Anders Celsius, who said, let's make freezing water 0, boiling water 100, because we can calibrate a thermometer anywhere around the world with water. Fine. And let's divide it by 100. Why? Because we like base 10, and that's handy. If we were in the base 12 scale, we could divide it up. Celsius said, let's set 0 and 100 according to this scale. Well, the Planck scale simply said, let's set 0 as the coldest temperature and 1 as the hottest. You could have made the hottest temperature 10 or 1000, right? Or any number in base 60. But Planck, seeking this ultimate simplicity, let's make it 0 to 1. And I find that delightful. And yes, it is indeed very, very strange, and it's rather bizarre, but there we have it. Some business for us, friends. We're going to have 2 more, episodes this year. We're going to have one on Monday the 5th, and then we'll have Monday the 12th, and we will go on hiatus, as we do each year for the Christmas break. The break between semesters, all of you know that I'm a professor of science education at the University of Arkansas. The break between semesters was when I spend time with my family, my telescope, my dogs, and when I do my writing on things like the Star Mentor book. So after the 12th, I will take a break, and we'll be back and join you on January 16th. Next week, when we get together, we're going to talk about the best telescope. Around this time of year, people all over contact me and say, I know nothing about astronomy, but I've got a nephew, uncle, husband, wife who's interested in astronomy. And what's the best telescope for someone to start in astronomy? What's the best binocular? So we're going to have a show, the best telescope, next week. And then when we come back on December 12th for our final episode of the year, we'll wrap it up, talk about one of the Einsteinian constants. We're going to talk about the fine structure constant, 1/107. Feynman himself, Richard Feynman, said every physicist worth their salt should write the number 1 on their blackboard and think about it every day, because we have no idea why. And Beatrice says, yay, telescopes. And yes, Beatrice, great, thank you. So I encourage, if you have friends who think about astronomy, and Mike says, I own the best telescopes. Looking at the rig on your picture there, Mike, yes, I want to come over to your backyard sometime soon. You have that looks like a lovely plane wave unit on a lovely mount there. And I suspect that's an ME mount or something like that. And oh my gosh, yes, you do have telescopes. But we're going to talk about, how do you start someone in astronomy? A lot of people want to get someone started. They don't want to buy too much or too little. They say, the typical conversation I have is, I want to buy something for my child and I want to spend this much. And I don't want to point them. I want to encourage them in the hobby. I don't want to get something lousy that they're going to be disappointed in. What we in the trade call a hobby killer. And we talk about, gee, what should we have? And so next week, I will plan on doing the show from the Explorer Studios. So Paul and Kent, be aware. Doc will be in the house next week, and we'll use some props from the showroom floor, and we'll talk about best telescopes and what can I get, what should I buy. And we're going to use, there are many wonderful manufacturers. We're going to use stuff from the Explore Scientific Inventory, not just because they sponsor my show, but also because I have a lot of their equipment. And people ask me all the time, well, you teach astronomy. What do you use? I use an awful lot of Explore Scientific equipment in my professional work. This is what I train young teachers in astronomy. This is the equipment I use to train them to teach astronomy to youngsters. And I'll encourage you, Christmas present for somebody, don't forget to get them a copy of Star Mentor. And if it's in science education and astronomy education, go ahead and download a copy of my free book, Astronomy for Educators. It's really astronomy for everyone. If you've got someone in your house who wants to learn astronomy, will learn about it, and you'd like to do fun projects and hands Astronomy for Educators is used in more than 8,600 schools in more than 65 countries around the world. I gave it away free, and it now serves more than 350,000 students every year. That's a conservative number. I suspect it's more, over 500,000. But these books, friends, represent my life's work, my entire history of helping people learn about our wonderful hobby of astronomy. And for those of you who own telescopes and binoculars, Star Mentor. If you've got a youngster in your life, if you know someone who's homeschooling, or you know a teacher who's struggling to teach astronomy and space science because so few of us are trained in astronomy, the Astronomy for Educators book is just for you. And Astronomy for Educators, you can put that into any search engine. Astronomy for Educators, Daniel Barth, it'll pop right up for you. The address is from ScholarWorks, and the University of Arkansas publishes it, gives it away free. Star Mentor is available, of course, on Amazon, and it's part of the Patrick Moore Practical Astronomy series from Springer, so it's available worldwide at fine booksellers everywhere. There we go, friends. We'll see you next week, and we'll talk about what's the best telescope for the holidays. And we'll do that, and then we'll finish up with one more episode in 2022. And so I'm excited. Tell your friends, if your friends are like, oh, you know astronomy, what should I get Junior for Christmas? Help them to tune in next week. And I'll, of course, post on the Astronomy for Educators space. Harold Locke says, my sci-fi is fun reading. Thank you, Harold. I appreciate that. My sci-fi is written for the young adult reader. And the idea was writing a science fiction book. If you were there, you could do the same thing as the characters in the story. You can email me, astronomyforeducators@gmail.com. I do respond to every single email I get. So if you have a question about astronomy equipment, or to get your kids for Christmas or something else, you're welcome to contact me. If you have questions about the quantum foam, or if you have an idea for a future episode, something you'd like to see on How Do You Know, I encourage you to write to me. And by all means, to see you folks for the next couple of weeks before we all break for the holidays. Thank you, everybody, and clear skies.